Okay, good morning, everyone, and welcome to the Salmon Forecasting Workshop. My name is Matt Falsey. I'm one of the two instructors for this. I'm a USGS employee and a assistant unit leader at the Idaho Cooperative Fish and Wildlife Research Unit at the University of Idaho. Prior to my current appointment, I worked for the Oregon Department of Fish and Wildlife, where I helped forecast salmon returns, mostly of our Oregon coastal Chinook populations, as well as developing some of the decision-making frameworks around harvest in light of the forecasts that I and others were putting together. So it's a real pleasure for me to have been invited here to share some of the work that we all do in the salmon forecasting realm. So just for logistics, I think you all know where the bathrooms are out there. Please, if you feel free to just stand up and do whatever you need to do. Hopefully we can get this to be kind of informal as we get going here. There's water in the back as well. What else? So the broad overview of this is that we're going to do these introductions right now. There's two other people who are going to introduce themselves. Then Dr. Sherrill will lead off with an overview of forecasting. Then I'm going to come back and speak for about an hour with some slides and do a little bit of code as well. But you don't have to have a computer. I think it'll be totally fine if you don't have that. But if you want the code, you can get it from this right here, the site we're seeing right now. So then after I wrap up, we'll have a break for 20 minutes. We're going to have to time that well because refreshments will be provided. So it's not just any 20 minutes. We will be sure to get you there at the right 20 minutes. Then when we come back, Dr. Sherrill will do some fancy stuff with you, and then I'll wrap up with some decision analysis kind of things. So that's the broad scope of what we're doing today. So one last thing, just by way of introduction, there's too many of you to really introduce yourselves, but maybe what we can do is just like a little show of hands here, just so we can all figure out who we are. So please raise your hand if you are a graduate student. Okay, only two, the brave and bold. How about a state employee? Okay, federal employee? Yeah, anybody from the tribe or representing tribes? Wonderful. Who else? NGOs or consultants? No? All right. Here's the real important question. Who here is actively engaged in performing a salmon forecast? Nice. Yeah, I see a little bit of this. I understand that. Very good. Okay. Well, great. Well, thank you all for coming. This is hopefully will be participatory to the extent we can do it. We have a lot of things to talk at you with, but things will be better for everyone if you can pipe up with questions, comments, interrupt us. There may even be opportunities, especially for those of you who are engaged in developing forecasts, to share a little bit of your perspective. I think that will be welcomed by everyone. So please don't hesitate to tell us what you know. We know a few things here, but we certainly don't know everything. And so any participation we can get from you, I think will be really enriching for everyone. Yeah, so with that, I will step aside for a little while. The next person I want to introduce is Sean Simmons. He's engaged in some forecasting work and also helped organize all this. And I will let Sean complete his introduction.
Yeah, thanks, Matt. Yeah, welcome everyone. This is exciting. As Matt said, I helped organize this, and a little bit of background on me. I'm the president-elect of the Washington, British Columbia chapter. And maybe I'll tell you a little bit about sort of the background, how this came to be, because you see behind me, there's the Salmon Prize banner. So at last year's conference in Bellingham, we had a plenary speaker, Dick Beamish, come and talk about how is it at a time we're seeing an epic collapse of salmon on the West Coast, we're seeing at the same time an all-time high in the North Pacific. And then we don't know the answer to that question is both a challenge as well as an opportunity. And for geeks like me, it's like, oh, there's mechanisms out there that you haven't quite teased out. And for my day job, I run online competitions for anglers. So I'm quite familiar with competitions. So I thought, what if we set up a competition where instead of anglers competing for the longest fish, scientists or teams of scientists could compete to see who could get the best predictions. And that really was the origin of the Salmon Prize. And so this will be the the third iteration right now. And we also have an online team of people who are participating as part of the Salmon Ocean Ecology meeting, which kicks off tomorrow. So this is actually being hybrid. So we'll have folks being able to ask questions online. So I passed one of these out for everyone. If you're interested, what you learned today, you want to apply it, sign up. It's free, $200 for the first 5 completed competitions. And we've got $5,000 in total prizes if your predictions come through. Now, this will be interesting, this one. This is the Sockeye International. So there's 14 runs you have to predict. There's 8 from Bristol Bay, 5 from the Fraser, and then the Columbia is just one sockeye prediction. And we've already collected the brood tables, so you can basically use that as a starting point. But we want teams to explore other ways in which you can integrate additional sets of data, maybe remote sensing data, maybe machine learning methods. What are the various methods you can come up with developing forecasts? And what we're hoping is if we can get enough participation with enough diverse teams, we'll get a wide range of hypotheses coming through and models that are used to build it. And the hope is the cluster covariates right at the top that are the best predictors will start giving some real insights into what might actually be driving some of these things. I don't know if it's going to work, but that's sort of the idea behind the Salmon Prize. So without further ado, I think pass it off to Mark, and good luck, everyone.
Salmon Prize. That's a clap for Sean, not for me. Okay, good morning, everyone. My name is Mark. Dr. Sherrill is really only something somebody calls me on rare occasions, so feel free to just Mark, hey you, guy up front, whatever. I am the assistant unit leader for fish at the Washington Cooperative Fish and Wildlife Unit and an associate professor there in the School of Aquatic and Fishery Sciences. Prior to coming over to the co-op unit program about 5 years ago now, I was with NOAA Fisheries for 16 years, where I did do some work on salmon forecasting, run returns, et cetera. So as Matt alluded to, this is really meant to be an informal meeting group. It's a workshop, much more so than a course. We've prepared some materials that we're going to present to you today, but this is an opportunity for you to engage in conversation with us, with your neighbors. If you don't understand what we're saying, you need me to stop, slow down, et cetera, just raise your hand and be like, hey, could you just pause here for a minute? Or what did you mean by, et cetera, et cetera. I appreciate that some of us have been doing this for a long time, so some of these terms, concepts and whatever are going to be relatively familiar. For some of us, it's going to be brand new. It's going to be a little bit like drinking from a fire hose. So sit back and relax, try your best. If you want to follow along, hopefully most of you have received an email from me this morning. The materials are all here. For some of these slide decks, like this group right here, if you're trying to navigate, it's the arrow keys if you'd like to follow along. So the first thing I'd like to do today is just try to give sort of what, this is largely my conceptual overview of sort of what the forecasting life cycle looks like. And there's going to be an opportunity for all of you to participate. So in general, I've got a laundry list of things, but basically when we start forecasting, I think a lot of people think about like, oh, we're right into the numbers here. And what I always tell folks is that that's really late in the game. There's a lot of work to do before we start dealing with numbers and math and stats, that sort of thing. So the first one is to really sit down, and if you're not the one who's actually been charged with doing this, but instead maybe you've been brought in as a consultant, you should really be spending a lot of time chatting with the folks who are involved, trying to understand and assess what is it that they're trying to accomplish with these forecasts. Okay, so, oh, all right. So as far as this goes, oh, that's a, okay. So as far as, assessing who's doing what and how we're going to do this, the first thing is to really ask, okay, who is involved? Is this entirely an in-house operation? Does your group have all of the data, all of the personnel, all of the computing resources and whatnot? Or is this a much broader consortium of people you're working with? When you think about areas like the Columbia, lots of groups involved there, many states, tribes, feds, et cetera. So just having an understanding of who is involved is really important. The next bit I think of is trying to think about what is the goal of the forecast? Are we really thinking about harvest management? Or are we thinking about this in a conservation context? So in areas like the Columbia, both of these come into play. There is some amount of harvest that goes on there, and so people have to set goals for harvest. But obviously, there are a lot of ESA listed stocks, and those require some conservation concerns. There are triggers in place such that if numbers fall below a set level for a certain number of years, different management triggers get enacted. So the goal of the forecast is also important. Are we thinking about trying to manage for escapement or manage for a constant harvest rate? These are not the same thing. Different systems work in different ways, so your forecast is going to be affected by those goals as well. Are we talking about preseason or in-season forecasting? So preseason, like Sean was just talking about here, let's try to come up with a prediction now for what's going to happen months down the road, versus in season where we're starting to actually see runs coming in. Maybe there's test fisheries, and we're trying to use that information to figure out what's going on very much in real time. So a forecast of a year or months versus forecast of days or maybe a week. Second part, okay, so we've got a pretty good understanding of who's involved and what we're trying to accomplish. Now we need to start gathering information. So big one here is actually who holds the data, not where do I find them, but who are the owners of the information. Is it all freely available? Could you just click a button on a website and download that? Or does this involve people with proprietary interests and they're holding that information very close to them, and you have to come as a, an equal partner or maybe a subservient partner and ask for permission to use that information? Are we dealing with harvest plus escapement? Is it just escapement, just harvest? All that sort of information comes into play. And for those of you who are working in agencies or even with tribes as well, you may very well actually have different groups that deal with harvest and different groups that deal with sort of the fish bio data. So thinking about those. Age composition. We'll talk about this a little bit later after the break. This is a very important part of it. It is very difficult, absent maybe pink salmon and perhaps coho, to do a decent forecast without age composition. And I once had someone come to me and say, we had this really long conversation about how they wanted to develop a new forecast for a Chinook salmon fishery in the lower Columbia. We got well into the conversation and I started asking about age composition and he said, well, you don't have that. It was a really quick call. Thanks for calling, and I hung up, sort of thing. So, the information that you have will affect what you are going to be able to do. And for a lot of this, that requires age comp. Do you have information on intermediate life stages? So things like smolts, fry, that sort of thing? Or are we just dealing with adult data? Adults are what most forecasts are largely based on, but in some systems, you may have more detailed information that could be brought to bear, and it could be very useful to you. We'll talk about this some more. Sean even alluded to it earlier today. Are you just trying to base your forecast off of the biological information? So thinking about things like sibling regression, which we'll touch on a little bit here. Or are you also trying to bring in some sort of environmental predictors? PDO, ENSO, upwelling, temperature, counts of pinnipeds, all these sort of things might be information that you need in a forecasting context. Importantly, though, you should be giving thought to where these forecasts of the covariates are going to come from. So if I need to know what the temperature in the ocean is next year, and we haven't measured that yet, we need essentially some way of obtaining that, a forecast essentially of a predictor variable. So these are things to think about as well. Okay, so we've got our information, we have some objectives. Now we need to decide on how we're going to go about doing this, some sort of modeling framework. You're going to hear about a bunch of them today. Could be a sibling regression, could be an environmentally based thing, could be a hybrid of those two. Are we going to consider both observation and process errors, sort of a state space framework? And if this doesn't make much sense to you right now, it will after the break, so just sit tight. Do we have information on just counts? Again, do we have information on age composition? Do we have maybe mark recapture estimates? Can we fold all of this together into something like an integrated population model? We'll talk about those a little bit more after the break in detail. Okay, got this going. Now we need to think about time horizons. And there's sort of two aspects to time horizons. So the one is presented with a time series of, let's say, total returns here. So this is catch plus escapement. And we're sitting there at the end of this time series because someone has come to us and says, hey, we need to start developing a better forecast model for these things. How are we going to do this? We need to predict time 31 here, 32, 33 maybe. So what are we going to use to be able to make this forecast? And there's two aspects to that. One is you need to consider how much of the data available to you are you going to use to fit your models, and how much of it are you going to use to evaluate the skill of your forecast in a prediction context. And so this one I've sort of labeled balanced, but perhaps overly optimistic, meaning 30 data points here, we've taken half for fitting and half to evaluate our forecast. And I call it, so that's balanced. And when I say perhaps overly optimistic, what I'm getting at here is that 15 years in your fitting may not be enough to really fine tune your model. You may need more information than that. So a different situation might be something like this, where you're really focused on the fitting part of it. Now we've got 25 data points that we want to use for fitting, but we've only reserved 5 to evaluate the skill of our forecast. So that may challenge us in the evaluation phase. If we have different models we're trying to compare, different stocks, that sort of thing. So trying to decide what's the balance of fitting versus prediction, that's a really tough question, and there is no answer to that. Ultimately, there is an answer, but this is largely trial and error. And this is something that usually comes from the groups that you're working with or other practitioners in the region. So Matt's not going to tell you the answer to this. I'm not going to tell you the answer to this. This is largely something that has to be evolved. And the system that you're working in, you may start to focus in on this really thing. Some of this may be prescribed by management. The government or whatever might come in and say, we need to evaluate predictions based on 10 years. There, you're done, okay? Otherwise, it's this kind of push-pull. How much data for fitting, how much for criteria and evaluation. Then the second part of this is a consideration of how many time steps in advance do you need to produce a forecast for. So in the salmon world, which I think most of us are here to talk about, this is largely 1 year ahead. I can tell you that about 20 years ago, I was trying to push a forecasting paper through review process at a journal. And one of the reviewers very pointedly asked right up front, what good is a 1 year ahead forecast? Clearly, this person didn't know anything about salmon or salmon management and that sort of thing. It was because largely this is where we're at. But there are some situations where people would like to say, how about 5 years? We need a 5-year forecast. So in that case, if you needed a 5-year forecast, you would need at least 5 years of data reserved for your evaluation thing, and you might need more. If it was 2, you're going to get 4 forecasts out of there, et cetera. So it's sort of balancing on this effort. How much for fitting, how much for evaluation, and how far in advance do we need to produce these forecasts? Okay, we've got a model figured out. We figured out how we're going to do our time horizons. Maybe we've set several, and now we're going to start gaming the system. So we need to basically fit our models and generate a forecast. How are we going to do this? Well, in statistical modeling, there's multiple ways. One might be a Bayesian context. You'll hear about some of those models today. If you're doing this in a Bayesian context, what are you going to do about priors? And if this language is coming over your head at the moment, Matt's going to get to this in just a little bit. But basically, is there other information from different systems, from different years that could be brought to bear on your problem at hand? What software are you going to use? You're going to do all this in Excel? Can be done. People laugh about that, but Ray Hilborn, my postdoc advisor, still uses Excel for a lot of things. And especially in an educational context, if you're trying to explain to folks what you've done, Excel is a really good way to do it. You might choose something more advanced like R or other things. We'll talk about some of those. So then we're at a situation now where we've produced a forecast, and now we want to know how well we're doing. So this is our evaluating our fit and our skill. Matt's going to talk about some of these aspects a little bit later this morning about accuracy and precision. Oftentimes there's a tension between those two. We'd like to be entirely accurate and entirely precise. For those of you who are shooters, being in that bullseye all the time is a good place to be, right? Model comparisons. So do you have a suite of models that you're looking to compare the skill of? The Weather Service does this all the time. The weather that you get on your phone every day is not the result of one model. It's the result of an ensemble group of models that they've been working on and weighting to some degree or another. Oftentimes, you will see people fail to consider a naive model, but I often encourage people to throw that in. Meaning, what if I just think of a sort of a naive model as a guess? The WAG, everyone heard of what a WAG is? Wild ass guess? Yeah. Or, I mean, a very simple model if we're thinking about in a statistical framework. Maybe your naive model is like, I'm just going to take what last year's return was. That's my forecast for this year. Turns out, actually, that's a pretty good guess. In a lot of situations, there are actually really formal papers that have been written and evaluated, and that turns out to be pretty good. Okay, so we've gone through this problem. Now, this stuff is, you can imagine all this stuff is sitting on your desk, on your computer. But now you have to turn around and present it to a group of individuals, fishermen, managers, other research scientists, et cetera. So reporting results. Really important here is that communication aspect. What is it you were telling them and what does it mean? And we'll talk about some uncertainty in this workshop today. Uncertainty tends to be a really hard thing for people to get a handle on. Like 0.1%, 13%, those are actually hard numbers for people to be. It's amazing, but oftentimes rational numbers can be much easier. 1 in 10. Your average person grabs 1 in 10 much easier than they do 10% or 0.1. So think about these sort of things. Uncertainties, we were just talking about that. Are you just presenting a point estimate? 1,234 fish. Or is it that plus or minus something? Do you have multiple uncertainty envelopes you're considering? You have a 90% uncertainty, 80, 60, something like that. This is something that I'm a huge advocate of is your stuff open and reproducible? Open means that can everybody else see what you're doing? Is it publicly available either during or after the process? And is it reproducible? Meaning if I sit down and do something and get an answer, can the rest of you all show up independently, do the same analysis and get the exact same answer I did? This is becoming more and more important, especially for those of us who work in government and or when we're considering laws. So think about this, a lot of the work that I do, Matt, and probably many of you in this room directly affects things like ESA, Magnuson-Stevens, et cetera. And if I've pooched all of this bit, that's going to get me and other people in trouble. So just think about that. Okay, lastly, think about this as a life cycle. We got to step 8 here, but basically this is refine and repeat, meaning basically do a post hoc evaluation with yourself, your group, other constituents, et cetera. How well did we do? I think I've even got some of this thing. Were mistakes made? What can we learn from this process? Now we should probably be thinking about updating our data. And if we're thinking about priors, do we need to update our priors? Because next year we're going to have to go through this exercise again. Or maybe we're going to be asked to apply our forecasting skills to a different system, different species, different geographic location. Update our models. Maybe we've decided that, yeah, we've been using this sibling regression for a long time and it seems to work, but over the last few years, it's really breaking down and this is not working. Maybe we need to consider something else. Maybe you just read the coolest paper in the world last week and they showed something that would be worth considering. So I think always being open to new information is a good idea. Okay, so that's basically what I have. So I'll just back up here one step so we can sort of see what this forecasting strategy does. This is my worldview. I know that I've missed some things and I've certainly glossed over others. So this would be an opportunity for me just to ask the audience at large, are there things that I have mentioned that ring particularly true to you? Or maybe things that I haven't mentioned that you consider in your cases? Everyone should know that I'm really comfortable sitting in silence for a long time too.
One question I have, you were talking about bringing in data and determining whether that's going to go towards fitment or towards projection. And I'm not super familiar with forecasting for salmon returns. I'm just wondering why that same data can't be used for both.
That's a great question. Typically, and this afternoon, I'll show you some examples of, yes, where basically you generate a 1 year ahead forecast. And then once that data becomes available, then you incorporate that into your model and then you punch forward again. Typically, though, you can't start at the very beginning and do that. You could, but your model needs a little bit of data before it can actually become sort of reasonable and skilled. It's like fitting a linear regression to 3 data points.
So you're talking about creating your own model as opposed to using data that you're collecting out in the field to compare the accuracy of your model versus.
I'm talking about both. So all of these data presumably are coming from your system. Yeah, but at some point you have to make a prediction for next year. And then you want to make that prediction, then you can update your models. But at the time you made your prediction, you want to know how good or bad that was.
Okay.
So when Matt starts talking about things like root mean square error and maximum absolute deviations, those sort of things, you need some number of data points to actually calculate those statistics over. And if you've only left yourself 2, you don't have a very good, right? You're comparing apples, oranges, pears, bananas, instead of kind of apples, 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 that sort of thing. Yeah, but that's why I was sort of alluding to, that question is tricky. Some systems are really, kind of easy in a sense. Some pink salmon systems, for instance, get on an odd or an even year cycle and you have a really pretty good idea of what's going on. Anything else folks can think of that I missed or it's germane?
Well, the thing that jumped out at me most is that point number 8, and it's certainly, I run a small tech company, and the build, measure, learn cycle is that iterative process, and it's not what you do the first time, it's what you do the 7th time that you really start getting your mojo. So I was wondering on that refine and repeat, have you seen any really best practices on that, or where have people done it really well? It's once you finish the experiment, you learn from it. How do you then take that and reincorporate that again into the cycle?
That's a great question, Sean. I would say that is entirely open-ended. People will have, some people get very lucky. Okay, they've done this once, they produce a forecast for next year and they were within like 2%. And everyone's like, good God, man, you should be doing something else, not working in the salmon world because you're really good at seeing the future. And then the next year they're off by 400%. And everyone's like, you really do need to find a different job. So this is a situation here where I feel like teams and colleagues are really valuable because, I maybe went through this entire process by myself. Well, maybe not 1 and 2, but you're sitting here and you're kind of isolated and you're like, hey, that's why having some of this stuff like open and reproducible. Hey, everyone, here's what I did. Here's how I did it. This did not work very well. What am I missing? And in a lot of the trades, oftentimes that stuff's kept very secretive, right? Because it's like, well, we're not going to tell everyone else how we did this because we're really getting close. That said, there is, in business, a lot of people talk about the 80-20 rule. Anyone familiar with this? Yeah, you get something to about 80% of where you think it should be, and you're like, there's version 1. And you send that out and it's buggy as all heck, and all you get back are comments from everyone about how it doesn't work. Oh, okay, now we're fine. There's other people, so you can imagine kind of your skill and ability hitting some sort of asymptote. And at some point, there's some small margin out there that's just probably never going to be attainable. But there are some folks that will sit there and agonize over chasing that margin and trying to close that gap down. And that can just be really self-defeating and self-deflating. So I would caution against that aspect as well. At some point, we all have to sit down and do our job. And so being able to actually just say, okay, I think I've learned from what I did last year. Here's what I'm going to change. Here's what I'm going to do different. We'll learn again next year. This is sort of that adaptive management scenario that people hear about.
Yeah, like fail fast, fail cheap.
There you go. Yeah. Fail intelligently. There's some really great podcasts out there about there. Yeah. Anything else from folks? Yes.
Yes, more of a shameless plug. On number 7, results. Once again, a shameless plug. I do have a poster here. My office, we do run forecasting for our spring Chinook and summer Chinook. And we use Shiny app, which is the R-based program. And that is our way of reporting our run forecast. And yeah, so that is our way. We send our link out to all of our partners, and that is, they can go easily access our run forecast. It's live, and we don't have to be pestered. to put it lightly, for real-time accurate estimate of our run forecast for our facilities. So, yeah, it's a really quick way of doing that. And it's just one of the easy ways. It used to be a once a week update, and now we don't get the daily, hourly calls. What's the run gonna be? What's the run gonna be? So.
Yeah. Thank you very much for sharing. If you don't mind, would you share your name with us so we can look for that poster? Thank you. Yeah, so Shiny is a great application. That's, if you are a comfortable R programmer, you don't even need to know a lot of R programming per se. There's a lot of templates that are available to you, but Shiny apps are a really good way to do these sort of things. You can display all kinds of information. It's readily available. You just open it up in a web browser and it's all right there. And as she was saying, you can, that stuff can be updated behind the scenes on some basis, and then people can just go and click around and see what they want. Oftentimes there's even scenario things, you know, slider bars that you can play around with and those sort of things. So yeah, thank you very much for sharing that. That's a great way. Yeah, Kevin.
Maybe you're gonna get into this later, but looking at the evaluation piece, and wondering if you could talk to the kind of metrics you might recommend for how you evaluate. There's lots of different ways you can look at your prediction, how accurate or not accurate, but where some standard way to look at that, or different models might come out better or worse depending on how you evaluate them. So I don't know if that's something we get into later, or if any.
Yes is the short answer. We will get to that later. Matt's going to cover some of those. In general, though, there are sort of two different ways of doing it. One are in sample. Those would be using things like AIC, BIC, Schwartz criteria, some of those. And then there are others that are out of sample, and those will be like leave one out cross validation and some of those. And Matt's going to speak to those this morning as well already. So yeah, I'll just hold off on there and don't want to spoil Matt's show. Anything?
We're having folks online asking if we can speak up, so I got a microphone.
Okay.
If anyone's got a question. I guess no more questions.
Any other questions or comments about any of that? Nope. Okay, well then I think I will hand this off to Matt. There we go.
Okay, so there's a few objectives I have for the next exactly 1 hour. I believe that is when we're going to break for refreshments. So I will try to keep my eye on the clock, but you know, I expect you all to just stand up and walk out at 9:40. But some of the objectives I have for this next hour are to review some broadly review some forecasting techniques. So these are like forecast math kinds of things. It's not going to be all inclusive. There will be things like Mark is going to focus on in the next session that or at post break that I'm not going to even touch here. But I'm going to go over some model technique. We're going to talk about model complexity in terms of the variables that we're using to enhance our forecast and how we're going to deal with that complexity. What are some of the problems of having very complex models but not a lot of data? And so one of the first things we'll do with some code is just real quick look at some stuff there, show you how you can prove to yourself that a complex model is actually a bad thing. So I want to make that point as abundantly clear as I can. So we'll use some code for that. And then we'll discuss the leave one out cross validation. This is an out of sample forecast accuracy evaluation and the various metrics that we can use to assess how good that forecast is. These are some of the things that Kevin is talking about. All of this, however, is going to be really high level. It's just really to kind of wet the whistle. And I think one thing to maybe just kind of set the scene for what I'm about to show you is to think about Mark's number 2, which was collect information. We're not really going to talk about that here. A lot of you maybe are doing this yourselves or working with others that are engaged in just enumeration of fish, harvest rates and collecting samples for ages. And those details are very important. And if you happen to be working in a system where you can know the number of fish that are leaving a river system, you should probably be using that information in your forecast, right? So there's kind of a boutique element to all of these forecasts. There's site and species and indeed time specific. And, I don't have the time or really even the desire to go over all those kinds of unique real world situations that are actually very important. So I want you to keep that in mind. This is going to be kind of high level, but like another really important thing, since Sean was mentioning this one here, the one thing that I was immediately thinking as well, do we know how they were collecting the data for that? Because maybe they changed their sampling protocols in the middle of the time series. You're just seeing a list of numbers, of abundances maybe, and you don't know if there was some change. Maybe you don't know if there was some change in how they were collecting information and making inference about those abundances. And if you knew that, you might want to use that in your forecasts. If you know something about the uncertainty, you might be able to weight certain numbers more than others. And if we have time, I can share some code with that. It's not on the site right now, but incorporating known uncertainty is also a very smart thing to be doing. And I think Mark is going to touch on some of these concepts later on when he gets the integrated population model. So anyway, this is just a long way of saying that what you're about to see is super high level, just conceptual. And some of this might be kind of boring if you're deep in this stuff. And if not, maybe we'll have a fun conversation about it. So complexity happens mostly because we have at our disposal many types of covariates that we can use to enhance a forecast. Yet we don't necessarily know which ones are going to be the most informative or the most predictive of escapement or abundance or whatever we're forecasting. And so this sets up a situation in which the analysts will be tempted to use every possible covariate at their disposal. And it invites people to incorporate many, many covariates into the analysis. And it isn't merely the mere number of covariates that are at your disposal, such as the things mentioned here: ENSO, snowpack, salinity, temperature, copepod index. The list is long. So it's not just that, but you can also entertain quadratic effects, right? Which means that as the predictor gets larger and larger, maybe there's an increasing relationship with abundance, but then it starts to decrease, right? You need to have some temperature above freezing, but not too hot, right? There's a Goldilocks sweet spot in there. So the quadratic effects are maybe something you're thinking about. And then maybe there's an interaction between some of these variables, right? And so the number of terms you can put into your statistical model is extraordinarily large. And this is a real problem that I want us to think about. And it'll be kind of the first subject I'm going to go over. So here's an example of maybe a small set of kind of universally available predictors. These are all ocean metrics that NOAA produces. This is frequently called the stoplight chart because of it's almost red, green, and yellow. It used to be more of like the stoplight colors, but anyway, this is, you may hear people speak about the stoplight chart. So this is stuff that NOAA puts together. We got time, year on the columns, and then down the rows are different variables that NOAA is tracking out in the ocean. And then they get rated, ranked in terms of their extremity relative to historic, and then also with belief about the way in which salmon are going to respond to these things. And the little numbers in there are just kind of like the ranks. So if you've got, I don't know, 25 different years, the ranks are 1 to 25. And so we all have access to this. I've tried to highlight the website where this is available. And so this is maybe a good place to start for considering ocean dynamics into your forecast. But you need to be smart about how you do this, right? And it tells you right on here what are the months associated with this. It says May to September. I know in the room you can't read this, but it tells you what months they're measuring this variable over. It doesn't really tell you what spatial domain it's being measured over, though. So maybe you want to change that. You have some belief about when your fish are getting into the ocean and when you think they're going to be most susceptible to death, and thus want to measure these variables at a specific time and spatial domain. So, and you don't know, right? If you knew that, you would just put it in there, right? You would already be using it, but because you don't know, you will be tempted to change the temporal domain and maybe the spatial domain over which these covariates are measured. So again, we're faced with just too many almost things to use in a forecast. So why is this a problem? This is a good thing in general, but it can also be a bad thing. So let's just take a moment to talk about what happens when your model is, quote, too complex. So here's just 3 examples of models fit to the exact same data set. So you got an input, so this is some sort of covariate, and an output. The output would be salmon abundance. And so there seems to be some sort of pattern in which there's an increasing relationship between the output and the input over a certain range of the inputs, and then it seems to flip almost and kind of comes back down, right? And so I'm speaking of this right here. But you could, if you wanted, fit just a straight line to it. You know, you're going to explain, it'll use some of the input information to explain some of the output. It's not a horrible idea. But that model's not too good, right? Because it's biased on the left and on the right, because your model would overpredict the output on the left and on the right, and it underpredicts in the middle of your input, right? So there's bias associated with this. We can flip now to the other extreme, and this may seem ridiculous, but will next in some R code show you that it doesn't take a whole lot of ingenuity to get a model to hit every point and have an R squared of 0.99. This is actually possible. But I argue this is bad. Why is this bad? I ask you. Yeah. Yeah, can't predict anything. I mean, you could, so I'm going to ask you to clarify, because you can technically predict something, but I think you mean that the accuracy is bad?
Yeah, it performs well on the test set, but when it comes to the training set, but when it comes to the test set, it'll be pretty off.
Right, that's it exactly. So think of it this way. Just imagine how weird nature would be if there's this up-down relationship of your input and your output. How freakishly bizarre is nature if that's what's going on? I just don't think that nature operates that way. So like it's likely, and this is what the gentleman is referring to, that this model is overfitted, and thus if you had a new data set, you would not have this exact same line, right? You would have another set of squiggly lines, and it would be different. Here, however, you would probably get the same, because I actually simulated this data from this model. And so if we did this over and over and over again and got new data points or new data sets, this model would still continue to be a pretty good predictor. And indeed, it would work better than this one here, because it's too low here and it's too high up here, right? So part of this just has to do with almost like a philosophical belief in how nature operates and what is the level of actual complexity at play. And complexity is often conceived in terms of the number and the interaction of all of our input variables, but just consider in this case of a single input, the kind of complexity implied by the relationship given here. That's nuts. Okay, so that's not a good model. And thus the Goldilocks zone, right? That's what the thing we're looking for here. Not too simple and not too complex. So how do we get there, right? How do we begin to find out when we're at the right level?
With that too complex one, it'd be really hard to predict kind of where the next one could be, because it could be up higher, way down lower. But in the Goldilocks, I would assume with a few more data points, it would continue to drop off just a little bit before beginning an upswing.
Yeah.
But obviously, that's a very general kind of analysis of the prediction, but is that kind of what we're looking at there with the differences?
Yeah, I mean, I'm not conceiving of this as a time series. You know, this is because here the input is maybe some ocean variable, PDO or something. And so when PDO takes on a new value, it can be anywhere randomly on this x-axis. And so we might see the same PDO. So say this point was observed in 2005, and maybe we get the same value for PDO in 2025, right? But then the output will be different. So yeah. So, for the purposes of forecasting through time using like a time series analysis, Mark will talk about methods of doing that. So it's like the domain of these variables are important, I guess, like, like how we're considering their variation. But essentially, the ability to predict with this one is going to be compromised by it being too fit to the peculiarities of your particular data set. And so when we get a new data set in the future, it's too fitted to the existing data to be useful for making a good prediction in the future. Yeah. I'll show you this. We got a real simple code that I'll go through to illustrate this point. So this is going to be like really basic. I maybe for some of you, and for others, maybe this is just like stats 101 all over again, and maybe that's going to be painful, but there's some use to this. Okay, so what we're going to do is we're going to look at how we can overfit a model, and I'm going to prove to you, I think, that we can generate pretty high R² values just by adding more and more variables. And indeed, we can do this by adding more and more variables that are not related to the actual data generating process. So I'm going to eventually show you a paper I did in which we used Major League Baseball stolen bases to predict salmon. And to prove the point that you can get these models that will actually use that and fit to a model, but it's crazy, right? Like there's just no way that that's real. So I'll prove to you with this code we're about to do that you can overfit a model quite easily and get an R² and an ability to predict like this that sounds kind of good, but it can't be right. So I just want to maybe express how that happens. And so the problem is really just using the R², the traditional R², and I'll show you with the output in R in a moment. But this problem that I'm describing doesn't actually occur with adjusted R². And we'll take a look at that. So I'm going to switch now to the code that you have available called overfitting. And it's really simple. The whole thing is right here. Let me zoom in a little bit. Does that look okay to you guys? Is that all right? Zoom in more? More? Okay. Can't see it all, but there's really not a whole lot here. Okay, so I am going to do the following. We're going to generate some predictors, and I'm going to call them X. And they're going to happen to be multivariate normal, but none of this matters. I'm just generating numbers to use to predict something else, right? So the exact way in which I'm doing this really makes no difference, and it has nothing to do with my point. So I'm just going to kind of blow right over that. We're just getting numbers, okay? Then we're going to use those numbers to make a prediction, and that's Y, our response variable. And the particular form I'm using is like a linear regression. There's an intercept, which is 20. And then there's a beta coefficient, -5, which is going to get multiplied into our first variable, plus another coefficient, +0.5, which I'm going to multiply into the second variable that we generated above. Yes, sir.
They got a link? Okay, perfect. Somebody was asking for the link so they could see it online. So
Okay.
It looks like somebody just sent them on, so it's all good.
Right. All right. Thank you. Okay, so we've actually, if you look at the details up here, we created 20 variables, 20 X variables, but we're only using 2 of them to make our prediction about Y, the first and the second X. And then we're going to add on some noise as well. This is really just simulating data from a linear regression with 2 variables in it. That's all this is. Very simple. Okay, then down here, we're going to, so I have to use this mass to do the multivariate normal. Okay, now we're going to look at a linear model, LM. This is just a simple linear regression. And it's got the two variables in there as predictors, x1 and x2. So this is the correct model, right? We generated the data using x1 and x2. We generated y using x1 and x2. Now we're just going to fit a model using x1 and x2. And so let's take a look at what comes out of that. So we get in this case, with these randomly generated data, we get a multiple R squared of 0.41 and an adjusted R squared of 0.38. Okay, so just real quick, why is this not 100%? Right, this is the exact right model. We know that this is the correct model. Why isn't this 100%? Yeah, we added noise. Exactly, right here. Right there, we added noise in there. So because of this, our predictors do not perfectly predict. There's extra noise that is going unmodeled here, okay? But if we look at all these tables, we'll see that we have correctly quantified the amount of residual variation, and this is a perfect model. I'm just going to ask you to trust me on that. Okay, but now let's look at what happens when we run the same model with the same two inputs, x1 and x2, part of the true model, but now we're going to also add in this third variable. And this third variable, if you look up above on line 3, that was not actually used to generate the data. So now we're predicting with a variable that is actually not related to the data generating process. And now watch what happens to R squared. Remember, we had 0.41 and 0.38. Well, maybe we got to go back to more significant digits. At 0.4121, now it goes to 0.4142. So it went up, very small increment, but it went up. And so to make my point more, perhaps we'll just jump right to this next line. And I'm going to use the first 20 variables now. I'm going to use 20 variables now, only 2 of which were related to the actual data generating process. And now we'll see a bigger bump in the R squared. It jumps up to 0.615 now. Okay. So this is weird. Maybe, I don't know. Is this weird? I don't know. I want you to realize that it's possible to get pretty good, some measures of fit that are misleading. But notice that the adjusted R squared does not correspondingly increase because there's a penalty for adjusted R squared for the number of terms you're using. So I can demonstrate how that works down here, where these R squareds are coming from. Well, you have this in the code, but just so there's less mystery about where these numbers here are coming from, we can calculate it out right here as well. These are 3 ways of getting the adjusted R squared. One of them is just lifting it literally right out of the output we were just looking at. And here are some ways of calculating it by hand. The reason I'm emphasizing how to calculate adjusted R squared is that this is the one that's more useful, right? Because it's got a penalty baked in for the number of parameters you have in there that you're using. Okay, last little thing with the code, and then I'll jump back into PowerPoint, is another demonstration of a really good model that is totally nuts, totally crazy, okay? So what we're going to do here is I'm going to use the third variable, which was not related to the data generating process. This is just a random variable. This is stolen bases or the price of rice in China. It has no bearing whatsoever on our response variable. And what I'm going to do is I'm going to make a polynomial function out of it, right? So I have all these different letters here, which are just that variable raised to a different power. So it's this variable squared, variable cubed, variable to the 4th, to the 5th, and so on. And so with this, really it's just a single variable, and we're just taking a mathematical function of it and then using that to make our predictions. And now we also get a very nice, this is a respectable R squared. And this is a variable that had nothing to do with the output. Okay? So this is the nature of the problem of having a model that is overfitted. So now let's switch back into how do you deal with this? Yes, sir. No. I mean, Mark, anyone else, is there a good argument? I don't know what it is, if there is one. Yeah.
Well, oftentimes there is an interest in how well your predictions relate to the outcome. And that's where something like an R-squared or correlation coefficient comes in hand, but I wouldn't value future model. For the exact reasons that it should.
Okay. So let's run through how we deal with this kitchen sink problem, right? You throw everything but the kitchen sink at it. Well, we've demonstrated some problems of having models that are too complex. So let's transition into ways of dealing with this problem, because it's a legit problem. You've got all these covariates, you don't know which ones. What are you going to do now? Well, this is my only math slide here. I know this is brutal, but it's actually, there's a little pattern that we're going to see in here. It's actually quite simple in a moment, I hope anyway. There's a few things that I want to chat about with respect to how to make some models for this situation. And what some computer scientists will use, and gets into machine learning techniques, are these quote unquote shrinkage techniques. Okay, so this is where you've got a coefficient, kind of like the betas in a multiple linear regression. And you're going to be suspicious about those numbers that are away from zero, right? Because as they diverge from zero, then that means that they're having some sort of effect. And if you're concerned with overfitting, you might believe that the number is too big. So what these shrinkage techniques do is they take those coefficients, those betas, and they push them back towards zero. This sounds weird, right? But this is what a lot of these machine learning techniques do. And I'm going to show you how these techniques perform relative to some more traditional techniques. So I want to just take a moment to outline a few different ways and a few common names that people apply to these kinds of techniques. So what I really want to focus on are these shrinkage techniques. But for you to understand the math that's given there, I want you to see the pattern to just ordinary least squares at the very top. So there's this equation there, and all that is talking about is the average squared difference of the data points and the prediction, right? So it's just squared error, traditional stuff. And you'll notice that repeats in all of these three techniques, right? It's the first term is the same as just ordinary least squares. But what gets added on are the thing that gets multiplied into the lambda, which I can point to here, that guy right there. Okay, so that's taking the absolute value of all of those betas, coefficients, adding them all up, and it's multiplying it by a factor that's going to push them all closer to zero. Right? And so the question is, what is the proper value or magnitude of shrinkage that we want to apply to compensate for our concern for overfitting? Well, there's cross-validation techniques that canned packages will use to figure out what the proper lambda will be. Okay, so this is stuff that the computer will do for you, or computer scientists really have already done for you. And we'll talk about where this comes from when I get to the cross-validation component. And then, and this is called LASSO, least absolute shrinkage and selection operator. So often used in these scenarios of many data at your disposal. You're throwing the whole kitchen sink at it, but you know you've got a problem. So this is the way you try to tackle it. Ridge regression is very similar. It's basically the same thing, but instead of the absolute value, it's the coefficient squared. And then finally, elastic net is this hybrid between the two. It's got elements of both in there. And there's a user-defined variable between 0 and 1 where the user has to define how they're going to trade off the penalty for, or the magnitude of shrinkage that they're going to apply. Is it just the absolute value or the squared value, which is always positive, right? But you know, the trade-off between lambda 1 and lambda 2 is defined by a user-defined input alpha. Okay. All right. So these are seemingly useful tools for dealing with the model complexity problem of all the variables that we have at our disposal. In a moment, I'm going to show you the performance of these tools to a very traditional one, just sibling regression, right? So sibling regression has a mathematical form. So we have the abundance at a certain age at a certain time, y sub dt, is some intercept plus a coefficient times the abundance of the previous age at the previous year. Okay, so this is like 2-year-old fish from last year being used to predict 3-year-old fish from this year. And so it's the same cohort. And that's why it's called sibling regression. So all you have to do is you develop these models, these relationships of sibling survivals or sibling abundances, and you add them all up across all the different ages, and then that's the total abundance. So I'm thinking like Chinook here, the total abundance across all ages that are going to come back at a certain year. Okay, so you just sum up all the YDTs. Now you've got uncertainty around each individual YDT, right? You're basically have a regression for the abundances at a certain age at a certain year. And then as I'm saying, you're going to add all those things up to get the total. So you've got uncertainty at the level of individual ages, the actual regressions for the age. Well, some very handy stats theory comes to the rescue here in determining what the overall variance is. Because variances are additive, we can merely add up the individual variances of each age, and that's the variance of the total. So the variance of a sum is the sum of the variances. Okay? The variance of age 2 plus age 3 is just the variance of age 2 plus age 3 plus a covariance term here too. So this is the theory for how we can get a variance estimator around sibling regressions. Okay, just a little bit more to help build your intuition on sibling regressions because it's so important in this world. Here's a common way of displaying your data for a fish that matures at multiple ages. So we've got run years down the rows and the different ages of the fish on the columns. Okay, Mark will talk about what happens when you have uncertainty in these numbers when he gets into his state space modeling. But for now, this is just super traditional here. We're going to ignore all of that, and we're going to assume that we have perfect information about the ages, which is obviously false. We never had that. However, if we have a table of abundances by year and age, the idea here is to take the 2-year-olds in 1975 and use that to predict the 3-year-olds in 1976. So that's like a point on the graph that I have right here. And as we just iterate through time, we will build a plot. And then it's just simple linear regression. Right? And maybe you don't want to use regression. Perhaps you want to have some other asymptotic function. This is quite reasonable, that maybe you get a lot of age 2s, you don't get a corresponding bump in age 3s, or some sort of asymptotic relationship. And so that's totally admissible. We can do that. You got to have good data to support that decision. But nonetheless, we're just merely talking about a relationship between siblings. That's all this is. But very common and indeed a very useful technique for modeling, for conducting a forecast. And again, Mark will go into this in a lot of detail when he gets the stage. Okay, so we're going to throw another model into the suite of models that I'm going to show you and have a comparison against one another. And this is artificial neural networks. So this is an AI technique. So artificial neural networks are modeled around biological neural networks in which there's neurons that receive all these inputs from their neighbors. And if the activation frequency of the little firings of all of these neurons exceeds some threshold, it will kick off a signal in the downstream neuron. And this is a very simple way of describing how our brains work. And that same kind of idea is implemented in artificial neural networks, in which we have all these nodes here are just the different variables: PDO, sea surface temperature, copepod index, freshwater stream, temperature, whatever. And they get propagated into these, those values get pushed into these other nodes, but there's some weight And then another weight, as you sum up all the inputs, another weight gets applied and it goes into another function. And then all those functions get weighted and wrapped together and then mapped into another function. This is starting to sound a little weird. Gets mapped into another function, and then you get your output. Well, there's a mathematical way of describing all this. The details don't matter. What I really want you to see is that there's like a lot of stuff in there, right? It's kind of like a lot of parameters, actually, if you think about it. It's a ton of parameters. And we don't often have a lot of data. So the folks in AI, where you work for Google, you have access to billions of search results where they type in something and then they actually click on one thing and they spend time there like, oh, that was actually a search result that they wanted. So the folks that are using these neural networks quite effectively are dealing with a very different kind of data than we have in the salmon world. We do not have billions of replicates of the process, right? We get at best maybe 20 or 30. So begs a question of, are these techniques useful for us? One of the advantages they have is that they're useful for modeling nonlinear systems and identifying complexity. So, you know, what is the curvature and the interactions among all these variables, right? We don't know, but these models are really great at discovering it. You can put in many covariates and look at their interactions and even have these feedback loops going on where this is like a time series analysis is essentially what it can do. So you can have these autoregressive components of the neural networks that is seemingly really useful for salmon forecasts. However, the cons of this is that because of the complexity in that previous slide, we don't really have any English language method of describing what's going on. It's forever locked up in this model that is so complex, we can never really mechanistically explain it. And that's problematic for a scientist who wants to understand mechanisms of nature. I point out that it's totally useless for hypothesis testing for the reason I just described. And some people will say that these things are great because they're, quote, universal approximators, meaning that you can, no matter what kind of real world function, however crazy it may be, you can essentially discover it with these neural networks. However, this is also their Achilles heel for the reasons we were already describing about model complexity. And so if you don't have a lot of data, they can be very problematic. Furthermore, what they do is they will withhold a certain amount of the data, and the user has to decide how much. Typically about 20% gets withheld. And there's an iterative process of fitting this model, like basically making guesses at all these different WJIs, all these beta Js, and all of these things. Guesses, you can think of it as just guesses are made. And then you look at how close does the output match the thing that you're trying to predict. So you're holding some data out and you're looking to see how closely does the output match the true value, the actual number, which is known. And so as the model progressively gets fitted in an iterative process, it will eventually overfit the data. So there's this other data set that it's looking at to see, okay, now that I'm fitting to this data, am I overfitting? Like, is my prediction power for the data that's been withheld, at what point does it start going down? As you withhold some data, you predict, it should get better and better as you're making better and smarter guesses at all the values up there. But once the model gets overfitted to the training data, the predictive performance of the out of sample data is going to go down. And then there's just, you know, a simple, okay, stop, shut down kind of a process in the algorithms that shuts down the fitting process so before the model gets too badly overfitted. All right, so I'm just going to show you now the results of a test we published a while ago on the use of artificial neural networks and all those shrinkage techniques relative to several other more traditional techniques, such as sibling regression. So my friend and collaborator, Josh McCormick, and I did this in, I think, 2015. And we're comparing a number of techniques here on real data I usually like doing simulated data, but we figured folks would have more relationship to it if it was actual real data. So we got some stuff on some abundances of coho salmon and Chinook salmon, and we used some of the techniques I just described to make a prediction. And we used leave one out cross-validation, which I'm going to go to in gory detail next, to determine the root mean squared cross-validation error. Okay, so this is just basically how close could we get to the withheld data using these techniques. And so this is artificial neural networks, elastic net, the lasso, the other shrinkage technique, it's just it's just the moving average. So it's just a very simple time series technique. Principal component regression, ridge regression. So this is the other shrinkage technique. Sibling regression that I already described, and a spawner recruit type analysis. And so what you see is that, there's no clear winner. There's a clear loser, which is the spawner recruit analysis. And those of you who've looked at these, there's often just a shotgun blast of points between spawners and recruits. And this, I should point out, this is a very simple spawner recruit analysis. So I don't want to shame this technique much. And in fact, Mark will show you how to get it out of the Stone Age, which is what we did here, and into a modern framework. There's still a lot of potential here. The value of it is that it uses density dependence and biological mechanisms that are quite plausible. But in general, it's kind of not clear exactly which one there's no clear winner. And indeed, some people might look at, well, we just want to know, like, how often is it going to be way off? So that's where the bars are really high. So maybe, although, like, this one's not terrible, occasionally it was just in another universe. Right? It was just way off. So, you can show these kinds of plots to people and let decision makers decide, how do they want to kind of trade off between being likely to get close versus small chance of being really far away. And when I get to the decision analysis part of this after the break, we'll talk about how to use that kind of uncertainty in a decision. I think it's really neat. Okay, I'm going to just pause for a minute and just see if there are any questions. And then I'm going to transition into leave one out cross-validation, what that is, and then we'll look at some code. But doing on time. We've got 20 minutes, so I'm really kind of running out of time, but I invite you to chime in. Okay, we're going to plow ahead. So we're going to get to this leave one out cross-validation code in just a second, and I'm not going to be able to describe it all because of time, but I think this will help you understand what's going on. So we've got run year down the rows, and then we have the abundance. This is the thing we want to predict. And then in this case, 2 predictors, okay? And so the idea of leave one out cross-validation is that you basically take a chunk of your data, except for one datum, and you fit the model to all of these data here. So that goes into the forecast model. And then what comes out is a prediction of the datum, which was never used in the model fitting process. And because computers are good at doing the same thing over and over and over again, we can just iterate this process every time, leaving out a new data point. And every time we're going to refit this model, and we're going to make a prediction for the point that got left out. Okay, so this is why it's an out of sample predictive ability, right? So these techniques, I think, are probably the best kind of way of testing the forecast accuracy. Because it's like a bona fide forecast. It's for something that is not used to fit the model itself, which I think there's a lot of value there. However, this suffers in a lot of time series analyses in which, like, you can't really get a prediction for the very first point if you're doing a time series analysis, because you have to have the string of points leading up prior to your predictive point. And so it makes no sense to have a time series model predicting the very first point. And if you leave out, like, this one right here, like, you're building a model here and then you're predicting the point there. And then how do you use all this data? I don't know, it's just kind of weird. So in time series analyses in which the whole history of points and the way in which they're related to one another is used for the prediction, this technique suffers. And then for the techniques in which we're not using out of sample, but rather like the in sample, so AIC, BIC, Schwartz criterion, there's a number of flavors of this, WAIC. These are great techniques for balancing complexity and predictive performance. However, they're all based on likelihoods. And for the neural networks, there's no likelihood. It's an iterative numerical process. So if there's no likelihood, you have no way of using AIC to assess model performance. Right? So I find leave-one-out cross-validation to be a really nice way of comparing tools, techniques, which are otherwise incomparable because they have just different fundamental math behind them. So, all right, this is gonna be a real whirlwind, so I apologize that this is gonna go a little fast, but I'm gonna show you how to implement a leave-one-out cross-validation. And the functions I have on the screen here will kind of help you see what's going on inside the code. So we're going to generate a correct model of Y, the response. This is like the abundance, the thing we're trying to forecast. And it's this function of one input only. Okay, so this is a real simple situation, right? One input, one output. But I'm sure some of you recognize this equation. Who wants to act like they're smart? Anybody know? Kevin C knows what it is. Yeah, Kevin, yeah. We didn't plan this. Yeah, so this is the Beveridge-Holt function. It doesn't matter. It's just that it happens to be a nonlinear function. So as x increases, y will increase and then asymptote out. So this is going to be the true model. And then we're going to also look at what happens when we have the wrong model, just a simple linear regression. Okay, so straight line relationship between x and y. Okay, so we're going to generate data from the true model. We're going to fit the true model and we're going to fit the wrong model. And then we're going to use some leave-one-out cross-validation techniques to look at and compare what we know to be the true model to what we know to be the wrong model. Okay. So switching now to a file you have available on Mark's GitHub, leave-one-out cross-validation.r. The whole thing is 47 lines of code. But you know, really most of the meat happens in 23 lines. So it's really not that bad. So I'm just going to quickly walk through this. So we have A and B. These are the two parameters of that Beveridge-Holt. So it's the slope at the origin and then where it asymptotes. We're going to generate some random predictors, uniformly distributed between 100 and 5,000. This is just arbitrary. This really doesn't matter. Now, this function I showed you right here is some details of technique, but you'll notice that epsilon is up in an exponent and it's normally distributed. So what this means is that y is log normally distributed. So the way I like to deal with this situation is to take the log of both sides. And when you do that, that epsilon drops down out of the exponent and it's on the real line. So it just becomes a nice way of fitting models that are log normal. I don't really like dealing with the log normal distribution. It's just more intuitive to me to just log it and make that thing go away. So you're going to see that in the code. All right, so that's what this is right here. This log of A plus the log of X. This is just taking the log of that equation I was just showing you. And you notice on the left-hand side, we have the log dot y. But then we're going to want to put it back on its native scale. So we got to exponentiate that when we make our prediction. Right. I know that was a lot, but let me just show you what this looks like. Generating some data. There it is. Okay, so B was 3,000. So you can see the numbers start kind of asymptoting out at around 3,000. A is 5, meaning the slope at the origin is about 5. Okay, so we've got, let me just look at, we'll just show you all these X's and Y's now. There's 20 X's and 20 Y's. So this code is going to start a loop, and we're going to just go through 20 different times in which we're going to take out one variable, fit the model to everything else, predict the one that we withheld. We're going to store the prediction because we're going to compute on that later. And then we're going to start the cycle all over again. So we're just really looping through all 20 points of data that we have here. So this pred here is just going to be a variable that's going to hold all of the output. You have to initialize a variable in R to hold outputs. So that's all that's doing. We initiate the loop, and then all I'm doing here to withhold a variable is using this minus sign. So we have this I as the index, right? So it's going to be a number. It's going to start at 1, then it's going to go 2, then 3, all the way up to 20. Right? So this is just the index in our variables of where the numbers are. Okay, so when we are going to use the minus that index number, we're saying take that one out. So when we do X, just look at X again. So you see X right here. Now we're going to do X. I'm going to set I equal to 1. And then I'm going to do X minus I. And then watch, you'll see that this number right here is going to disappear when I implement this. Boop, it's gone. See, so now it used to be 2,846, then 963. But when I do minus I, we just start at 963. Okay, so this is a way in which we can just pull out one number and keep everything else. We're going to do the same thing with our Y's, right? Because we're withholding the predictor and the predicted. And then we're going to fit a model and look at what we're fitting. We're fitting the withheld data, the .I. And this is the wrong model. This is just a simple linear regression. So this command LM in R is implementing simple linear regression. And then we're going to compare that to the true model, which is actually, it's a nonlinear model. So this NLS is how you can fit nonlinear least squares in R. And so this is going to fit the true model. So these models just get fitted, and then their components are stored in this output, mod 0 or mod 1. And then we're going to use those coefficients in that model to make a prediction. And when we make the prediction, look at what we're doing here. We're going back to xi. So this I was previously the value that we withheld. Okay, now we're going to we estimate all the coefficients, and now we're going to put that number, in this case, our predictor is going to go back in, and we're going to just multiply it into the coefficients, or we're going to use it in the function for the model we've just fitted. And then its output is going to get stored in this pred. We're going to compute on that later. All right, so we're going to do it here with the wrong model, and then we do it again here with the correct model. And yeah, I've got a plot of how this thing is working. So let's look at that. Might have to go like this. There we go. So what I'm doing here is I'm plotting the true value of Y, our predicted, like the abundance we're trying to forecast, and then what the predicted number is. So if they fall on the straight line, that means it got it exactly right. And anytime the points fall above, it means it over-predicted, and when it falls below, it means it under-predicted. And so what we're seeing is that with the true model, which is in green, the points are sort of uniformly on the top and on the bottom. So there's no bias, but you'll see that the linear model's got it all wrong. The points are above when X is low, and the points are below when X is high, okay? Because it's wrong. So all what you need to do now to enter this next phase of like assessing the predictive performance, we need to quantify this. Right now we have a picture, which is really useful, and I encourage you to look at these pictures, but we need to move beyond visuals. So we need to compute something about the discrepancy between the truth and the predicted. And so there's a number of things that we can use to do this. There's the mean absolute deviation. So all this is like, what is the true number, the true thing we're trying to forecast minus its prediction. Okay, and then we take the absolute value of that, because if you're wrong by being above and you're wrong by being below and you don't do the absolute value, then they cancel each other out and it looks like you've got an awesome forecast and you don't, right? So doing the absolute value is just looking at the deviation. Like, we don't care if it's above or if it's below. Like, here's below or above, we don't care. Just how far off the line is it? And so, yeah, let's just look at this one. So this is what I'm using, these numbers 1 and 2. This is the wrong model, and this is all the predictions from the correct model. And so let's just look at the mean absolute deviance of these things. Oops, sorry. Yeah, so the mean absolute deviance is 269 for the wrong model and 187 for the correct model. So why, again, is the correct model not have a mean absolute deviance of 0? It's the correct model. We know it's right. Error. Just good old-fashioned error, right? The model is not explaining 100% of the variation. If we had set, this would be kind of fun. I won't do it, but we could come back up here, right here, this R norm. So we're adding this noise. And here's the magnitude of the noise. This looks like a small number, but it's up in an exponent. So it's actually kind of a big number. But if we put that thing to 0, then that means that this model here would perfectly predict our outputs. And then when we refit, it would hit it perfectly. And so then it would drop down to 0. But because we have extra scatter that we're modeling here, even our known to be perfect model is not going to have a perfect prediction. I know that sounds weird, but it's sort of accurate. Okay, so there's just a couple other things I want to mention here. I've got 6 minutes. I'm going to let you get your coffee and cookies, but there's a number of flavors of these things. So we just looked at the mean absolute deviation. There's also the mean absolute percent error, MAPE. This one I really like. It's kind of more intuitive. It's looking at that absolute difference, just like we just saw, but then it scales it by what is the magnitude of the number we're talking about in the first place, right? So you see, this is just like what we had. Well, it's just the deviation, and then we're dividing by the actual number. So it's just scaling that residual by the size of the thing we're trying to predict in the first place. And then we average them all together. So the incorrect model has a negative 0.04 MAPE, and the correct model has a negative 0.005, like an order of magnitude difference. Now, if you're just looking at this order of magnitude difference, it might seem like it's huge, which is why I really encourage you to make a visual like I have here to plot it, right? Because if your intuition for these numbers is not highly calibrated, the pictures will help a lot. So there's a variety of these things. I'm going to stop speaking about it, but you have this in the code, and it ends with sort of the more traditional stuff, root mean squared error or mean squared error. This is kind of more 101 type stuff. I kind of lean towards MAPE and WAPE, but I'm just going to stop right here. I had a lot more slides I had hoped to do with you, but I'm glad I was able to show you how to do a leave one out cross validation. There's a lot more about model selection that I wanted to talk about, but I think we're going to, for the sake of time, I'm going to zip it right here and see. Yeah, go ahead, Mark. Okay.
There was just one, when Matt was alluding to over or under prediction. Here's the quiz time before the break. Okay, if over prediction, who cares about that? This is a real question.
Conservationists.
Yeah. Well, sorry,
I was gonna say people that, like,
yeah,
like one, people don't take.
and under prediction. There you go. Yes. So yeah, and there are some people who do care. I mean, as an analyst, we shouldn't. But in general, yes, you'll hear it from both sides.
Yeah, and when I get to my decision theory thing at the very end, we can go a deep dive on this and talk about how to balance the risk of overharvest and the risk of underharvest. And if we know what your risk tolerances are for these two different types of being wrong, we can bake that into a decision about how to implement a harvest regime. I think it's super neat. Kind of sits outside of forecasting, but I think it's kind of where the rubber hits the road on this stuff. So we've got 3 minutes. Anything else before we break for 20? All right, we'll see you back here at 10 o'clock.